Hello and welcome back to Differential Equations, section 5.1 on matrices and linear systems. So technically we are going to have a crash course in linear algebra to help us with the rest of chapter 5. These are the concepts that are used in taught in linear algebra, used to solve some very advanced engineering problems and so on, when you have systems of multiple equations. We are going to talk now about the systems, meaning that remember how we can convert differential equation into that characteristic equation, right? So you convert a system of differential equations into a single higher order differential equation, use the characteristic equation and so on. Now let's see if there are other ways to solve these systems. But before we do that, obviously because those methods would be using matrices, we have to review / learn, right? Depending if you took linear algebra or not. So we have to either review or learn about matrices. So what is a matrix? Matrix is a rectangular array of numbers, or variables, expressions, whatever, but numbers. So matrix is, come on tablet, matrix is a rectangular array of numbers. Again, doesn't have to be numbers, could be also functions. We have seen Wronskian, right, where you put the functions and the derivatives and then you compute the Wronskian, which is the determinant of that matrix. But for the most part, let's just deal with numbers now. And that matrix says rectangular, right? It can be square, but square is nothing else but a special rectangle. So we don't have to, define it again for a square, where square is a rectangle where a equals b. So now when you're talking about rectangular array of numbers, you can have your a, b, c, d, e, and f, let's say, and something like this would be known as 2 by 3 matrix, meaning 2 rows and 3 columns. You can also have A, B, C, D, E, F, G, H, and let's put R or W or whatever. And then, because I don't want it to be confused with ones like I's and L's, I'm trying to keep away from those that can be confused. Now, this would be a 3 by 3 matrix, and that will be known as a square matrix, and that's 3 rows and 3 columns. Something like this would be known as column vector. And like this, you can have it as a row vector. This one is obviously 2 by 1, and this is 1 by 2. Now, each entry of the matrix is labeled with its two-dimensional position. So if this is the matrix A containing elements lowercase a, then the top left would be A11, which stands for row 1, column 1. So each of these members can be denoted as IJ. Now, IJ, we can also call him MN, we can call him whatever. And I is the row position, and the J is the column position. So row 1 has A1, 2, A1, 3, A1, N. So it goes this way for N columns. And then you go to the next row, A21, A22, A23, A2N. Again, N columns, but that's N columns in the second row. Then you go the third row, and then I'm just going to say like this all the way down to the M row. AMN for the M rows, right? So M rows. So we can have any number of columns and rows, and that is governed by the system of equations that we are looking at, the size of the matrix. Now, I always mention that this is crucial for computer science, obviously, because in computer science you are dealing with arrays. Let's say you are using Java, and you have those arrays that you have to write in that keep the information, keep the data. Well, that's a matrix, right? Also, if you consider a photograph, let's say that it's digitalized, then each dot that you see, which is called a pixel, which is the smallest unit of the picture. I mean, pixels can still be subdivided with some new technologies and so on, but let's keep the pixel, just like we know that the atom is the smallest unit to make a molecule and make a compound, but then atoms can be still subdivided into subatomic particles, and you can go, you know, subatomic. Then you can also talk about the pixel being the main idea, right? You get 32 megapixel camera and stuff like that. That means that your pixel is the smallest unit, but then again, there are some technologies that would further subdivide that. So when we are talking about arrays and matrices, like this is the life for any serious computer science, because your programs will have data, will operate on data sets and so on. And you have to pull from those arrays, right? So you need to be able to count within those rectangular arrays of values, which are just fancy words for a matrix. And then also picture, right, with each pixel storing the color. So if you have this to be your picture, each square over here will have its own color, and the color is a number. So the array of all of these numbers, right? So computer knows which color to display in each one of these boxes, because each one of these boxes, right, as a single pixel can be green or yellow or whatever, and then green, yellow, or whatever have their numerical values in a system on the colors that are displayed right on the screen. So now any picture is nothing but this huge matrix of millions of entries of those numbers for color. And then, right, when it's in a raw format, when everything is, you know, without any compression, then you have a large file, like 30 megabytes or something. But then when you compress it into these smaller formats like JPEG or something, where the, you know, with the whatever compression ratio is used, then the matrices kick in to group all of these values into smaller. So obviously there is no way to do any kind of higher end programming without knowing linear algebra. It's just ridiculous to hope for it. So we are learning this matrix creature today, and if you already know it, then you're reviewing, and to realize how much it's used, and it's used in every form of engineering. And as I said, It's used insanely a lot in computer science. So what we can do? Well, technically, matrix as a rectangular array of numbers is just a bunch of numbers, right? And when you have numbers around, you can add them and you can subtract them and you can do all of these operations with it. Well, it works out that matrices can also be added and subtracted, but they have to be of the same size. And the very simple way of adding and subtracting matrices is that you add corresponding locations. Or subtract corresponding locations. So it's very easy for us to say that matrix A plus matrix B is equal to, and then you can just say Aij plus Bij, meaning that every entry of A that has a ij location is going to be added to the same location with the value B. Now, this very simple idea over here, 1, -3, 6, and 4, plus 9, 6, 0, and whatever, 4 again. So when matrix A has a position of A1, 1, that's a 1 plus 9. So 1 plus 9, -3 plus 6, 6 plus 0, and 4 plus 4 in a matrix. So we add matrices, term by term. Each location adds to its same location from the other matrix. Now this also works for subtraction, so I'm just adding that to the formula now. Oh, by the way, we did not finish this, so this is a 10, 3, 6, and 8, and that will be the result. Now if you have a subtraction matrix, you will do the same thing. Now they have to be the same size. So 1, 2, 6, 13, 9, and I don't know, -4, minus, let's go 6, 4, 3, 9, it doesn't matter, just put whatever, and 0 here, there you go. And now you will subtract. So notice that how the size of the matrix stays the same. We started with the 2 by 2 matrices, we got a 2 by 2 matrix. Now we're expecting the matrix to be 3 by 2 because we have 3 rows and 2 columns. So we have 1 minus 6, we have 2 minus 4, we have 6 minus 3, we have 13 minus 9, we had 9 minus 18, and we had -4 minus 0. And that collapses into, again, -5, -2, +3, +4, -9, and -4. So in order to add and subtract matrices, we have to have the same size matrix, and then you just do it between the same locations, right? So if I and j are 1 and 1, then the other one has to be 1 and 1 as well, and then those numbers either add or subtract depending on what you're doing with your matrices. Another one of these important properties is multiplication by a scalar. And that means that you are multiplying each member of the matrix by that scalar, so it will literally multiply into every location. Yes, you can, I guess, use the word distributes into every location. Now that's the way for us to scale matrix up or scale matrix down. So that's going to be 3 times, let's have a 2, 6, 4, well, let's make it 2 by 3, it doesn't matter, 7, 13, and -6, whatever. So this 3 will multiply every location of this parenthesis. So I'm going to have 6, I'm going to have 18, I'm going to have 21, I'm going to have a 12, and 39, and negative 18. And this gives us the now opportunity to define what subtraction is. See, subtraction is unnecessary operation because we can describe it through addition and multiplication with the constant c. So, and algebra actually deals a lot with these types of proofs and abstractions, mathematical abstractions, which why some students find it a little bit harder than they would like to admit. So a minus b is actually a plus negative 1 times b. And this is your definition for subtraction, where you have your, see, multiplication by a constant here. Your c is, from the upper definition, your c is negative 1, right? So this is the way to describe the subtraction through the eyes of addition and constant multiplication, which are the two rules that we outlined above. Do you have to do that? No, right? Because you still go and say that 2 minus, 4 is negative 2 and so on. Now, we do have some properties of matrices. Oh, I did not define a zero matrix. Holy nightmare. Let's do that first. Zero matrix is the matrix that only consists of zeros for however many rows and columns you have. So a simple 1 by 1 matrix that you are used to is just a number 0. That's it, right? A matrix of which is 1 by 1. And you know what to do it. If you have another matrix that it's also 1 by 1, let's say 7, right? Then you can add the two matrices. 0 plus 7 is 7. You can subtract the two matrices. 0 minus 7 is negative 7. And so on. So you can do all of these. You can do all of these things. But then if the matrices become larger, to have a zero matrix, that means you must have 0 in every entry of that matrix. You can still add it. You can still, we'll see later, you can multiply by it and get 0 on the other end as well. But we'll deal with that when we get there. So zero matrix is there. So now we have some properties. And we want to see that matrix A plus a zero matrix is 0 plus A, and that always gives you back A. Now you're going to say, well, what's the big deal? Well, it is a big deal, right? Because, again, you are now dealing with a zero matrix. That's not a single 0. That's a lot of zeros in how many places the matrix have. Another rule is that matrix addition is commutative. And then we also have the associative rule, where A plus B plus C can be also done if you do A plus B first and then add and then add C. So that's the associative rule. And then you also have the distributive rule. Now this distributive rule has two forms, because you are now combining the scalar quantity, which is your what you would call under quotation marks a regular number, and matrices. And they're always in notation separated by constants and coefficients and so on. Those are lowercase letters, and the matrices are uppercase letters. So, you know, if you have a sloppy handwriting and so on, you might run into issues with the notation. But the idea is that, you know, if you always keep capital letters on a different height than the lowercase letters, you should not run into that issue. So if you have a constant multiplied into a plus b, so it's clear to see in my writing here that this c is right. The c is a lowercase because the height at which I wrote c, right, is less than the height of a and b. So when you distribute this, it is ca plus cb. Distributive property, you can call it distributive property 1 as well. And the second distributive property is if you have two of the numbers. So say C plus D times the matrix A, then it's CA plus DA. It's also distributive property. So this is what we have, right, for these properties. We have all of these properties, and you notice that all of these properties are exactly the same as the properties you would have for basic numbers. All right, so the matrices are these rectangular arrays of numbers, and you know there is a visual component to it. You look at it and you say, oh, okay, it's a 2 by 2 matrix, it's a square matrix, right? Or it's 3 by 2, which means it looks like a rectangle, right? It's not a square anymore. As soon as you have more rows than columns, or more columns than rows, whatever way it goes, then you are going to have this situation where the matrix is not a square, it's a rectangle. And then we have something that it's called a transpose, which flips the matrix. So it writes rows as columns and columns as rows. So transpose of matrix A, written as A with a T as the exponent, is swapping rows for columns. I should add and vice versa, but I don't need to, because as soon as you put rows as columns, then columns have to become rows. So the transpose is the transpose of a matrix is that the rows become columns, which means that all you need to do is you need to swap the rows into columns. So if I have a matrix that it's let's say matrix A is 2, 6, 4, and 9, then A transpose is going to take 2, 6 and put it this way, and it's going to take a 4, 9 and put it this way. And I would say, well, only, you know, 4 and 6 switch the spots. In some sense, yes, but if you have matrix B that is, let's say, 1, 6, and 4, and then -3, I don't know, 5 and 9, whatever, then B transpose is going to have 1, 6, 4 as a column and negative 3, 5, and 9 as a second column. And if you take a look at it, you will say, oh, but 1 and 9 still didn't change the spot. Well, actually, no, 9 did change the spot, because 9 used to be in a third column. We do not have a third column anymore. So 9 did change. So technically only number 1, this AII position, which is 1, 1 position, stays unchanged, right? And the other positions. Now, those of you that are very observant noticed that 5 didn't change the position actually. So 9 did change its position because it went from a non-existing column in the new created row. Again, 9 switched from the non-existent, right, in this new B transpose. It went from a non-existent column, because the column is gone, into a newly created third row. But if you carefully observe number 5 entry, which is the entry 2, 2, then yeah, there you go. Now, in some sense, if you are going to use well, actually, just let's write the formula. A is Aij, right, in a matrix. Then A transpose is going to be Aj, right? So this is what we have in the formula situation. So 9 before was B, second row, third column, right? And now in a B transpose, it becomes 3, 2. And you can see that it's a 3, 2. It's a third row, second column. Where entry 5 was B 2, 2. And when you swap 2, 2, you still get 2, 2. So that's why it kind of stays. So anything that is on the diagonal will stay in its spot, and everything else gets to change. All right. So that's some introduction on these basic addition and subtraction aspects of matrices. Now we are getting into multiplication, which can be tricky if you're not paying attention. Now, we did multiply before, but we multiplied by the constant, and that constant multiplies every entry of the matrix. Should you say distributes on each entry? I guess you can. I guess you can. But now we are going to say matrix times matrix, and that is going to be a completely new subtitle here, because this thing is insanely important. I keep going back to computer science students. If you are taking differential equation and now you're looking at the concepts of linear algebra within, matrix multiplication is insanely important, especially for inverse of the matrix. If you want to have a search engine, if you have to have compression algorithms, if you want to have any tool to deal with sound editing, image editing, movie editing, like all of those tools are designed through some type of matrix multiplication and transformation of matrices. So you literally don't exist and are relevant in a field in any way if you are not able to go through these matrix multiplications, because that's how you create environments that change, on the larger scale. So guys, when I'm talking about computer science and linear algebra, I'm not talking about programming vending machines and programming some simple stuff. I'm talking about arrays, matrices. They have millions of entries, and you need to, or billions of entries, like Google search engine or Bing, if you are a Bing person, right? I'm talking about these systems that have insane amount of entries, and then you're supposed to manipulate those entries quickly and efficiently, which is what the compression and search engines and all of these things do through matrices. So what is the way for us to multiply matrices? So matrix multiplication is defined through multiplying rows of the first matrix into the columns of the second matrix, and there are strict restrictions on sizes of matrices that are compatible for multiplication. See, we don't have these restrictions for regular numbers. You can multiply any two numbers you can think of: positive, negative, even, odd, rational, irrational. We don't care what it is. You can always multiply. But for matrices, we are going to have this what do you call it? Restriction. There we go. You are going to have a restriction on the size. Now, let's quickly take a look at the multiplication algorithm. So, matrix C will be matrix A times B, and it's done when you take AI and multiply by BJ. Now, these are the rows of A times the columns of B, and you write them in the corresponding locations. Now, there is also another way to say that the Cij, which is a location of the product, and this is the formula that I'm going to circle, is the summation, k goes from 1 to p, of all a I k times b k j. Now, this is the formula that I want to box because, again, as a computer science person, this is what you will be programming into your software, right? This is the one that multiplies the entries. Now, let's take a look at an example of this. So to start off, I'm going to just take two square matrices because I don't want to have now to worry about the issue of compatibility of two matrices in terms of their size. So I'm just going to say I have 3, 0, 6, and 11 times -2, 4, 5, and -1, whatever. You can literally put any numbers you want. But I wanted 2 by 2 times 2 by 2 because they're definitely compatible. Now, this being my matrix A, this being my matrix B, I'm going to take a row of A and multiply it with the column of B. Look, row of A times the column of B, which are the row and column where I dump the answer. Now, I know that my answer is going to be 2 by 2. Again, that's experience and so on. You will know it as well when you get there. I'm going to take the row of A and put that onto a column of B. So what I'm getting, actually I'm going to make a step over here and then we'll have the solution. I'm getting 3 times negative 2 plus, which is the summation, 0 times 5. And I'm writing that in the upper left because I have the row 1 and a column 1. Row 1 from A, column 1 from B. So they're both 1 and 1. And that's why my dump location for the solution is 1, 1. C, 1, 1. Because I use the first row of A and the first column of B. Then they're both 1, 1. And the dump location for my answer is going to be 1, 1. Now I'm going to move 1 over. And I'm going to multiply the first row of A with the second column of B. So now I have 1, 2, and a dump location is going to be 1, 2, which means 3 times 4 plus 0 times negative 1. So 3 times 4 and then 0 times negative 1. Again, I use the first row and I use the second column, so that's 1, 2, and the dump location is 1, 2. Now we are going to go to the next row, and the next row is 6 and 11, and that's going to be multiplied into the first column. So now I have 2, 1 location, so 6 times negative 2 plus 11 times 5. And finally, 6 times 4 plus 11 times negative 1. When you multiply 6 times 4, right, plus 11 times negative 1. And now just do the arithmetic, right, in the... Now, obviously, students will go very quickly from but not writing the step. You just go directly into what the answer is, because you can keep this calculation in your head. 3 times negative 2 is negative 6 plus 0, so that's a negative 6 there. Then go to the 12 plus 0, that's a 12. Then we have negative 12 plus 55, that's a 43. And finally 24 minus 11 is 13. And that's the multiplication of matrices, right? You always multiply a row into a column. Now, because you are doing row times column, that means that the number of rows of the first matrix has to be the same as the number of columns of the second. Otherwise, they're not going to match. And you're going to have extra numbers floating around with nothing to multiply in, and you can't add them, and it just creates a mess. So the requirement for matrix multiplication is, now this is something that it's required. Number of because you go row time the column, right? So number of entries in a row of A has to be the same as the number of entries in a column of B. Number of, I want to call them entries. How about size of row? Of A must be equal to the size of column of B. So they have to have the same number. Now that is much easier to visually determine than to even write or even understand the requirement over there. When I have two matrices, A plus B, I need them to match the middle number. So this needs to be A by, let's say, M, and this needs to be M by B. Oh, let's use I and J. So the answer C will be I by J size. So the number of columns of the first matrix has to be the same as the number of rows of the second matrix, which are actually the size of the columns and rows when you look at it the other way. Let's take a look at multiplication then. If I have matrix 3, 6, 1, 8, negative 2, 0, and 1, 3, and 4, and that multiplied by, now, as you can see here, I am forced to have 3 entries to begin with, because I have 3 columns on the first matrix. I must have 3 rows in order for this multiplication to be possible. So we can have a column vector. We can just say x1, x2, x3, which is what we are going to do later in this lecture. But now I'm just going to work with numbers so we can get comfortable with the basic multiplication. So I can, well, actually, yeah, what the hell? I just put, no, let's do numbers. Let's go 3, 4, and negative 2, right? That's it, just that. So what do I have? I have 3 by 3 and then 3 by 1. I'm expecting the answer to be 3 by 1 because these middle 3's kind of cancel, and then whatever the outer one is. So please look at the formulation above, right? So you see that those inner 3's are canceled, those are your M's, and then your I and J, which are the outer ones, are the size of the outer matrix. So now, if M doesn't match M, you can't multiply at all. That is a restriction on multiplication, and you absolutely must follow that. Now, this should be a joke, right? You take these 3 and you put them on these 3, and that's your first entry. Then you go to the second entry and the third entry when you go rows down. Now, the way I visually memorized this when I was learning it for the first time is I said, oh, these 3 drops on the 3, and this 4 drops on a 6, and these 2 drops on a 1. Right? And then I just add those. So 3 times 3 is 9. So I have 9 plus 24 minus 2. 9 plus 24 minus 2. Because 3 hits the 3, and then 4 hits the 6, give us 24, and then negative 2 hits the 1, multiplies. Right? In my head, I just say hits. that's I don't know. It's just the way I dealt with it when I first, because all of this was weird. I mean, you're used to 3 times 7 is 21, and you move along, right? What do you mean you are now multiplying 2-dimensional arrays? And you can always make it more complicated. I'm just going to drop a word, tensor, and then some of you who take heavy-end mechanical engineering and heavy-end electrical and chemical engineering, you will know what tensors are. Trust me. So what we have here is now when you do this multiplication, you have 31 as your first value on top. So 31 is the top, and then you are going to now go 3 hits 8, 4 hits negative 2, and negative 2 hits 0. I don't have to worry about the 0. So 3 times 8 is 24. 24 minus 8 is 16 as the next answer. And then finally, I have, again, now 3 hits 1, 4 hits 3, and negative 2 hits 4. So that's 3 plus 12 is 15, minus 8 is 7. So I hope you all had 31, 16, and 7, unless I made a mistake in calculation, in which case, right, it's embarrassing, but it's also a reality, right? We make mistakes as well. So that's the matrix matrix multiplication, and I just want to now give a little twist on this problem that you see up here. So let's say you have a matrix 1, 2, 3, 1, 1, negative 1, 2, 4, and I don't know, 2, whatever. And then all of that times x, y, z, and all of that equal to, I don't know, 19, 6, and 4, whatever. See, what you see here is the system of 3 equations with 3 unknowns written in the matrix form. And when we write this in a matrix form, we generally call this matrix A. We call this matrix a column vector X, and we call this one the solution column vector B. And all of a sudden, this one becomes this major focus of linear algebra, equation AX equals B, which is actually a very interesting creature because the size of A, X, and B doesn't play any role in defining the type of the equation AX equals B, which means that you can have a system with 100 variables and 100 equations, and it will still be simplified the same way. Now, that's the power of linear algebra, where when you learned in basic algebra 2x2 systems, then in pre-calc 1 you learned your 3x3 systems, and then maybe you have seen 4x4 systems, maybe even 5x5 systems in your Lagrange multipliers in Calc 3, or you have seen them in partial fraction decomposition that has, you know, a couple of variables, right? You might have seen those larger, right? But you always deal with them on a case-by-case basis. This is how I solve 2x2, this is how I solve 3x3, and so on. Now, linear algebra gives you this equation that says, you know what, you can have 100 of them. It's still the same equation format, and then let's learn how to deal with this, because once you learn how to deal with this, you can deal with any size of a system, which is pretty amazing deal. And that's what linear algebra spends almost a third of its time, right, talking about these kind of systems. Now, what would this look like in its, let's call it, exploded form, right? Well, when you overlay x, y, z over the first row, you get x plus 2y plus 3z equals to 19. Because remember, when you multiply row by column, you get the top value. So that gives you this equation. And then you can go and multiply x, y, z, so that's going to be x plus y minus z equals to 6. And finally 2x plus 4y minus 2z equals to 4. Now this is a bad one because we could have canceled everything. So I'm just going to change this 4 into a 3 so I don't look simple, you know what I mean? Because if all of these were divisible by 2, then you divide the entire equation by 2 to reduce numbers. So now all of these equations, right, by changing that to a 3, all of these equations have their own state. Now, I need you...
Professor?
Yes?
Should be +2 at the bottom, right? For the last one.
Yes,
Plus
thank you.
2z.
+2. Yes, 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 yes. I got so hung up in advance thinking about this that and I can't multitask. All right. I have seen that 4 coming. And then just, yeah. Anyway, so what I need you to do now is to please immediately in your head, right, uh, stare at these two and make sure that you can instantly switch one to another. Instantly, right? Switch one to another. Because that's what we are dealing with for the rest of chapter 5. Your ability to convert the equations, right? To have a matrix and then subtract matrices, multiply by a constant, and then look for some weird stuff. We'll talk about weirdness when we get there. Now let's take a look at the system. Now, if you are faced with a system of equations, instead of cranking it down by hand, you can immediately write your system as a matrix and then run your calculator if you have the TI 83, 84, or whatever one of those TIs. If you have the calculator, if you don't have a calculator, there is a free app that you can download which emulates these calculators to their full potential. So obviously, I mean, I usually have to say, you know, if you are using the advanced cell phones, which are non-iPhones, but then this is differential equations, so right, obviously no one at this level should be using Apple technology for anything. So I'm not expecting any of you to have iPhones, but in case you do have an iPhone, you can always upgrade whenever it's time to get that menace behind you. But if you already, and as I said, you all should already have Droid-based phones. Again, you're sitting in differential equations class, so that should be common sense. You can download this free app, which will give you the TI calculator on it, and then you can run. You can take this matrix. Sorry, you can take this system and literally just erase the x's, y's, and z's and create a matrix that would look like this. 1, 2, 3, 19, 1, 1, minus 1, 6, 2, 4, 2, 3, and you should be able to enter that into a matrix in your TI 83, 84, whatever. You enter that into matrix, and then you use row reduce echelon form function, which is under matrix, of matrix A. That immediately spits the solution out for the matrix, unless there are, you know, unless the equations are dependent or something like that. I am going to actually try this real quick. So you go with the second button, you push matrix, and then you go to edit. You enter your 3x4 matrix, and then you just type in the numbers 1, 2, 3, 19. So 1, 2, 3, 19. That's the first row. The second row is 1, 1, -1, and 6. And then 2, 4, 2, and then 3. Once you have the matrix typed in, you go second quit. You push matrix, second matrix again. And now you go to math. And when you go to math, you see that you can find the determinant, the transpose, a whole bunch of stuff. But if you go down, you will finally get to RREF, row reduced echelon form, which is something you learn how to do by hand when you take a full linear algebra class. It's annoying, but it's possible. So RRF, and then you go second matrix, and under names, you pick your matrix A. And when you push enter, you will get a matrix that looks like this: 1, 0, 0, and then 22. 0, 1, 0, and then negative 12.1666 going forever. 0, 0, 1, 3.8333, dot, 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 dot. Now, what you could do is you could convert all of these into fractions, and you would actually get your 22, negative 73 over 6, and positive 23 over 6. But guys, these are your x, y, and z values for the system. And we haven't done any calculations. We literally, as you can see visually, right, picked up only the coefficients, including the answers as is, stuffed all of that into a matrix, and then did row-reduced echelon form, which spit out the answers. And now, since the first row represents x, the second one represents y, and the third one represents z, you see that 1 times x gives you 22. The other two are zeros there. So x equals 22. And then you have y times 1 over here, gives you a y for the second row, and that gives you this negative 73 over 6. And then finally z times 1, so z is the only thing that survives in a third row. Right? You would have a 0 times x over here, 0 times y over here, and 1 times z over there. So all of these are gone because they're times 0. The only one that survives is a z, and that's equal to 3.833333, which is 23 over 6. So it is very easy to deal with systems of equations if you know matrices, right? And you know that solving this system by hand would take a very long time, right? Not something like it's 3x3 system, so it's gonna take 5 minutes or so, but it takes you less than a minute to do it on a calculator. And in order for you to do it on a calculator in less than a minute, you need to know how to use calculator, and you also need to know how to convert your system into a matrix. Now, clearly, if you go to a system with 4 equations or more, you are going to run into pretty much similar time to enter everything in a calculator because you're adding just extra 4 numbers or so. But to solve it by hand, it's significant increase every single time. It's a significant increase. So we want to make sure that we are dealing with that. So that's our matrix multiplication. And there are some properties that we have to know. Most important, I have to write this in blood, multiplication of matrices is not commutative. Is not commutative. And a very simple reason is the one that requires the matrix size to fit that M. So in the middle. So let's say you have your matrix A of a size 3 by 4 multiplied into a matrix B of the size 4 by 1. This is going to give you an answer of 3 by 1 matrix. We're all happy there, right? Now, if you try to swap these two, I hope you immediately see the issue. Cannot multiply, right? Cannot multiply. Why can't I multiply? Because the inner numbers are not the same, right? This is 1, this is 3. Before they were perfect, 4 and 4. So cannot multiply because 1 is not the same as 3. Over here everything was cool because 4 equals 4. So matrix multiplication is not commutative. However, it is associative and it is distributive provided that the size of the matrix works. Now, someone might say, well, wait, professor, how about if we do 2 by 2 and 2 by 2? The numbers in a matrix are still not going to work out. So you have to be very careful about these things. However, properties that do work are ABC equal AB times C, and that's the associative property. To just write ABC like this, you have to have the middle match already. So if I have, let's say, 3 by 6 and 6 by 4 and 4 by 2, whatever, you see that A and B match at 6 and 6, and C and B and C match at 4 at 4. So if I multiply these two first, my answer would be 3 by 4, and I'm still good to go 4 by 2, because 4 matches 4. If I decide to go the other way, and I do this, then again 4 and 4, so the answer is 6 by 2, and I have 3 by 6 in front, so 6 matches 6, I'm good again. So if the size of matrices are such that you can do multiplication in the first place, then whether you're going to do it this way or you're going to do it this way first, it doesn't matter. You are not allowed to rearrange matrices. And that is something that is very, very scary, because sometimes, right, you get your BC, which is 6 by 2, that's your BC product, and now they say, oh, and I just multiply that by A. Hell no. No, you pre-multiply by A, because that's where the 3 by 6 is. If you put A here, it's going to be 3 by 6, and then A, it doesn't work, right? So because multiplication is not commutative for matrices, you have to now get into this idea of pre-multiply or post-multiply, which is something you didn't have for numbers, because 3 times 2 is 6, and 2 times 3 is 6, and 3 times 2 is 6, and 2 times 3 is 6, right? It's commutative for numbers, but not for matrices. So the words like pre-multiply by something is actually a very important term, right? Pre-multiply. And then you have the rule of distribution, right, where A, B plus C is equal to AB plus AC. So that's a distributive property. And again, given that these matrices, remember, the requirement of B and C is to be of the same size so you can add them. So if B is, let's say, 3 by 1, then C must be 3 by 1. Otherwise, you don't get to add them. So the requirement of these are to be the same size, and then A could be whatever the hell you want, 100, but it has to be times 3 to match the 3's that are inside. So now over here you will have your 100 by 3 and then 3 by 1, and 100 by 3, 3 by 1, and you can see 3 and 3, and it all works just fine. So distributive property is also something that matrices do have, but what we do not have is this situation with, yeah. Okay. The book definitely stresses the idea, right, of matrix commutative, right? Commutative rule does not work. The next idea is to define something that is called the identity matrix. And it is called the identity because when you multiply by it, you get the same value. So identity matrix I, and it goes like this. A times I is the same as I times A, ooh, commutative rule works here, is equal to just A. Guys, this is equivalent to saying A times 1 is equal to 1 times A is equal to A. So now this A is 10 or negative 100, whatever. So this I serves technically as number 1, but for matrices. And what it actually is a number 1 along the diagonals of a matrix. And one thing is that it's always a square matrix. So we would say IN like this. So features acts as number 1 for matrices, always, oops, a square matrix. That's very important. And then we say n by n, and that's how you get the notation IN. You don't need to write it twice. You just know if you say I2, it's identity matrix that is 2 by 2. And finally, always once on the diagonal, all other are zeros. So 2 by 2 identity matrix is, oops, is I2 is 1001. 4 by 4 identity matrix is I4 1000 0100 001 00001. I hope you see the diagonal pattern of this matrix, and the transpose of it is itself, because remember that for a transpose, diagonal stays where it is and the rest of the entries swap. But the rest of the entries are all zeros, right? So when they swap, it still stays the same. So identity also has that property, that transpose, that will never be used, by the way. I mean, in some proofs in linear algebra here and there, it might pop up, but you are never going to look for the you're never going to look for the inverse of the of the transpose of the identity matrix, because it's itself. All right. So now this matrix helps us find something that is called an inverse matrix, which is another big title. In linear algebra. And I did mention before that right? You have to know, you have to have inverse matrices so you can apply different tools to pictures and search engines and all of these kind of things. So if you want to go into serious computer science and work on serious software and development and so on, again, not programming vending machines and traffic lights, but programming high-end software, then inverse matrix is something that you absolutely must know. I mean, there is no debate there. Now, why is the inverse matrix so important? What is, right? What is it used for? How do we get it? Like all of these things. Well, first of all, we are going to understand that matrix multiplication, right? It's not commutative, and we still want to solve problems the same way we did in algebra. So let me give you an example of algebra solution to a problem. 3x equals to 12. So how do you solve this? Well, you multiply it by the inverse of 3, because 3 times its inverse is going to cancel down to 1, and then you have x alone. Right? To solve a problem, you are looking for the way to remove this extra 3 that it's in your way to have x alone. So that is achieved in this problem by multiplying by the inverse of 3, which is 1/3. And then that 1/3 will cancel the 3, leaving the x alone, and on the other side you get 4, and then x equals 4 is the solution. Now you can go and check. 3 times 4 is 12, so we're good to go. So you use the inverse. So 3 and 1/3 are inverses of each other. Now you have also spotted that with the notation of those negative exponents. And I hope you did, right? Because you have y equals x, and then you also have y equals 1/x, which can be also written as x to the minus 1. Right? Now, don't we remember that when you have a property of x to the negative m, that it's 1/x to the m? So if this m is 1, then you have your x to the minus 1 is equal to 1/x. So this 1/x is the opposite one of this one, because when I multiply them, they cancel and I just get 1. So now after all of this, which probably was maybe even unnecessary because you know all of this stuff, now I can go and write, remember my problem? A times x is equal to b. My entire problem collapsed into that. So technically, you are able to write this, having a system, you can write that immediately. You immediately know what your matrix A is. Now, why would matrix A be important? Well, remember what you're trying to solve for. You're trying to solve for x, right? You are looking to calculate x, and this x is given to you as a vector x, y, z. So if you are computing that vector, you have the numbers for x, y, and z all together. And that's really cool. Now, if we are to mimic what we did in algebra, well, it should be clear that all I need to do is to pre-multiply by A inverse. Guys, I can't stress it enough. Multiplication is not commutative. So you can't just say, oh, times A inverse on both sides. No, right? You have to write it in front of A, and then if you are pre-multiplying on the left, you will be pre-multiplying on the right as well. So now these guys cancel, and you have your solution x bar, vector x, is equal to A inverse times B. Now, guys, that's a regular multiplication, right? So if your problem was A matrix, I won't need this. So A times X equals B, and let's say this is a 3 by 3 matrix, then this must be 3 by 1, and the result must be 3 by 1. 3 by 3 matrix guarantees 3 equations, guarantees 3 variables, so you have x, y, and z in the vector x. Then your inverse matrix must be of the form 3 by 3, because inverse matrix is a square matrix, and it's going to go in between, sorry, it's going to go in front of each one of these. So you will have A inverse times A times X is equal to A inverse times B. Now this is 3 by 3, this is 3 by 3, this is 3 by 1, this is 3 by 3, and this is 3 by 1. These guys cancel, and here is your solution set, which is 3 by 1, because you have one number for, one entry for x, one for y, one for z. And what kind of an answer we're going to get out of this? We are going to get a 3 by 1 answer. So when you have inverse matrix, your solution for those systems is as easy as multiplying some numbers. Right before we multiplied 12 times 1/3 and we got 4. Now obviously multiplying matrices is a little bit more involved, but again, it's much faster than going through the entire, if you're doing it by hand. And at many schools, like many four-year schools, completely forbid calculators. So you can't cut corners, right? You can't get there very quickly. So now we understand where this inverse matrix thing comes in, and a very cool property for inverse matrix, which is what we are using actually up there, is that A inverse times A is I, and that's actually commutative as well. So identity, when you have the identity floating about, like, things become commutative. But again, that's just because identity is 1, all right? It's number 1. So it's very hard to kind of, deny that extra power, because that extra power is really there because of 1. Identity, right, is equal to 1. Okay. So now that we took care of all of that, we have just one more definition for the determinant, which is the one that you guys already have seen before. And determinant of A, which is just these absolute values. And if you have your A11, A12, A21, A22, remember, you go down the diagonal and then subtract the way up. All right, so down the diagonal and you subtract your way up. Good. Now, the way to, so clearly, I mean, you want to use calculators to grind through these things very quickly. Even if you are in a field, obviously, I mean, no one computes these things by hand anymore. Math majors, you should know this, all of these calculations by hand, by heart. But the rest of you, as long as you can get it on a calculator, because, you know, as engineer, you're not too much concerned about mathematical notation and everything being perfect. Most of you just stare at the graphs anyway. But, you know, math majors, physics majors as well, you guys are going to use these calculations and use these calculations within proofs as well. So you want to know how to compute these things. And here is the way now that I have the determinant, I can finally define a way to compute A inverse. Now that's a procedure. So given, let's say your matrix is, now this is only for 2 by 2, way to compute 2 by 2 A inverse. There we go. So given that A is A, B, C, D, right, then A inverse is 1 over determinant of A times D negative B negative C A. So guys, if your A is 7, then 7 goes there. It's supposed to be a D. There we go. If your B is 3, it becomes negative 3. If your B was negative 7, it becomes positive 7. So just change its sign. So you swap the diagonal, and then on this side you change the signs. So one diagonal, right, the principal diagonal, A and D, they get swapped values. And B and C just get a change in sign. Now this is the, again, there are proofs why all of this works and how it already, you know, how we get it to the end. But this is the way to, again, use matrix multiplication to solve those problems. So if I am to have, let's say, 3x plus 4y equals to 9, and that's a terrible, you know what, doesn't really matter. Let's put 15, whatever. And then you have your, let's say, negative x plus 2y equals to 7. I don't care. Put literally whatever. What happens is now you can quickly write your matrix A as 3, 4, negative 1, and 2. And you can quickly compute the determinant as well, because it's just going to be 6 plus 4, which is 10. Right, because you just go 6, minus and minus gives me plus, 6 plus 4 is 10. And you immediately have your inverse matrix. Your inverse matrix is 1 over 10, and now A and B will swap the places. So this becomes 2, this becomes 3. And then the other guys change their signs. So this is now 1 and this is negative 4. So my original problem was A times X equals B. When I pre-multiply by A inverse, I get X is equal to A inverse times B. But my A inverse is 2 over 10, negative 4 over 10. So 2 over 10, negative 4 over 10, 1 over 10, and 3 over 10. So that's my A inverse. And then vector B are just 15 and 7. And all I need to do is to do this multiplication. I have my answers because this X is XY as a matrix. So when this spits an answer here, blah and blah, the top number is X, the bottom number is Y. I'm actually going to, I have to go swap the cooling because I can see the tablet lagging. I'm going to ask you to compute this multiplication, and then let's figure out what these numbers are here. So go 15 times this and 7 times that one and see what we get. I'll be right back. I just have to swap the cooling. Does anyone have the numbers?
I got a 5th for the top one. I got 13 over 15 for the bottom one.
You said 1/5 and 1/3.
No, 13/15 for the bottom
Oh,
one.
13/15 on the bottom. Like this?
Yeah, but that's wrong. Sorry.
How do you know it's wrong?
Because 21 plus 15 is 36, not 26.
So, okay, so what should I write?
So I think it's actually 6/5 for the bottom one.
So 1/5 and 6/5.
Yes, I think so.
All right. So let's check that. That would be great if it is. So we have 15, so that's 30 tenths, minus 28 tenths, which gives us 2 tenths, which is 1/5. I agree there. And oops, I don't need this thing. And then I have 15 tenths plus 21 tenths is giving me 36 tenths. And 36 over 10, we cut that in half, we get 18 over 5. Unless I did something wrong.
No, you're good.
15
Sorry.
times 1. No, that's fine. I mean, again, you're learning, so that's okay. You will not make this mistake on a test. Those that are just connected just to be connected, obviously, right? They might easily make that mistake. You won't. So there you have it. So your x is 1/5 and y is 18 over 5. We did not do elimination, we did not do substitution, we did not do the graphing, we did not do the matrix in a calculator, right? Just by using those rules above on creating your inverse A, and then just pre-multiplying that inverse A into B. So we did one matrix multiplication, and the matrix B always has only one column. So all of this stuff becomes a joke every time. So now, I understand we only have 9 minutes, but now we are hitting our spot where actually differential equations can thrive, because remember how I didn't want to put the variables, I didn't have to do this and that. Finally, we're getting into matrix valued functions, which is when you get to stuff functions into matrices. So matrix valued functions. And now, what does that mean? That just means the matrix is filled with functions inside. So you can say that big matrix F is equal to some f11 of, let's say, t, f12 of t, f13 of t, blah, 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 f1 n of t, and then go all the way down and all the way down to get to fmn of t, right? So this matrix, you know, can have, if it's, let's say, 3 by 3 matrix, you can have 9 different functions inside. And you will find that, you know, this is all really well connected with the geometry. So give me a second. So if you are trying to rotate something in space, in a 2D space, whether it's a vector or an object and so on, as a computer science person, how do you code that when your computer only understands values of, right, coordinates x and a y, and can you know, light up that particular pixel? How do you code to rotate the picture 90 degrees or 40 degrees, whatever, right? Because you know that you can go to this photo editing software and you can rotate, you know, picture a little bit, or you know, do these kind of things. So there will be a rotational matrix for something like that. So this is, again, not the outcome for differential equations, but it's the example of what a vector valued function, sorry, matrix valued function is. So rotational matrix R equals to, and then you have your cosine theta, negative sine theta, sine theta, cosine theta, where rotational matrix to rotate object theta degrees. So what I need to do is I need to take, now guys, there is also 3D rotation, obviously. So do you want to work on a programming of the engine for a video game where, you know, the physics needs to look, it doesn't have to look realistic, but you need to rotate objects in the three-dimensional video game that it's projected on a 2D flat, you know, surface, which is your screen. Even for VR, I mean, you still need to rotate objects around. That's a third-dimensional rotation. It's done through rotational matrices, right? And the way you achieve that, right, is when you multiply the matrix you have with the rotational matrix, right, to obtain the new matrix, which is the new location for your object, right? The new way it's displayed. So rotational matrix is just, you know, an example of this. Now, we are not going to deal with rotational matrices or anything like that. We are dealing with obviously differential equations. But now, if I'm having a differential, vector matrix valued, if I'm having a matrix valued function, then then that matrix, that big F matrix, right, is a matrix of T, right? So that's some kind of Fij of T. So that's our way to say you have whatever matrix you have, and you can come up with the F prime of T when you simply differentiate every entry, which is differentiating every function inside the matrix independently. So now I have a way to represent the derivative as well, and, right, you guessed it, it becomes now a system of differential equations, which we can write also as a matrix. So what we have now is the first order systems. And you might not recognize it right away, but dx dt is equal to p of t times x plus f of t. There's your system. Now you say, I don't know if it looks like a system. And I just say, well, let's just write an example down and see. So I have d dt of the vector x. I'll just do two variables, right? So d dt of xy is equal to some matrix P. That could be functions, could be numbers. So let's just go with numbers to make it easy. And then here I have my x and a y. And then let's put this to be, let's say, 0 and cosine 4t, for instance. So I hope you can immediately see the correspondence, right? These two puppies are together, these two puppies are together, these ones and these ones, right? So I hope you can find the match of what each one of these is, right? And what we have. So now that we are there, right, I'm just going to write this in the what you would call the exploded form, right? So these two will go on top of those, and I'm just picking up the first row. That's dx dt is equal to 3x plus 4y plus this big fat 0. Then I'm going to put xy on this row, and I'm going to get for the bottom row dy dt is equal to negative x plus 6y plus cosine 4t. Now we just, rewrite this the way we're used to them. X prime is equal to 3x plus 4y, and y prime is equal to negative x plus 6y plus cosine 4t. This looks exactly like the equations we solved last class when we transformed them into that you remember what we did, right, last class, where we used that d notation, right? It was a dx minus 3x minus 4y equal to 0, and then factor out x and blah, 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 right? But now we just learned that if you have this system, you don't have to go the linear operator route. You can actually convert all of that into a matrix problem and then use what's coming up, right, in our chapter 5 to solve. And then obviously, right, this here is the solution, because when you get rid of all of these things, right, you will, whatever methods we are using, we're not there yet. I don't want to spoil the fun, but your solution will be, xy, xyz, or, if you have 10 of these equations, then you can go x1 through x10, for instance, instead of going x, y, z, w, right? And then you have to use other letters as well. So I hope that all of this made sense to you. I know that the minimum requirement for homework in our class is 5 problems. I will encourage you to solve all of the problems in this section, especially if you never took linear algebra, because you are literally trying to learn half of the linear algebra course in one crash course lesson, so that you can perform in chapter 5. So the good thing is that the 5 days, right, are coming up before our next class, and you have a lot of time to read this couple of times in a book, maybe rewind this lecture a few times on YouTube, and get comfortable. Get comfortable with matrix multiplication, right? When you think you got it, when you think you're good, just do one more problem. So you are really good with that. And we are going to use these concepts as we move through the course. I know that the class is over. This is extremely long lecture. I could have talked for another 2 hours just to fill in a lot of holes that we still have. I have office hours at 5:30, tomorrow at 12, but if there are any questions now, even though class is over, if you have to leave, you have to leave. But if you have any questions, I'm going to answer it now, actually.
So we're never really going to be given, like, asked to multiply two matrices that are like different, right? Because you can't move them around.
Exactly. So they have to fit.
Okay.
And most of the time, right, for students that learn the theory, most of the time you did something wrong because all of a sudden you can't multiply.
Yeah.
Good. Anything else? Okay. Well, office hours at 5:30. If you find anything, again, I'm encouraging you to do all of the homework, and I will see you next week.